Hello and welcome to lesson 32, our very final lesson on curve sketching. And this is the last lesson of this unit. So next lesson you have your summative assessment for unit 4. So today we are looking at special function families, and specifically with our learning goal, we are learning to sketch exponential, logarithmic, and trigonometric functions by analyzing transformations, asymptotes, and derivatives. So transformations you've already seen previously. And that's why I start with this question of what do you already know about the graph of the exponential function, logarithmic function, the sine and cosine function. So consider its shape, asymptotes, and any intercepts it has, because a lot of the examples you're going to see in this lesson are can be solved using just what we know about transformations. So curve sketching of special function families is not a major requirement of this course, but because we have seen derivatives of these functions and worked with them, I did want to make connections between what we already know about transformations to derivatives and the curve sketching algorithm. So if you aren't sure about the curve of any of these basic functions, please make sure you are using curve sketching tools to give yourself a refresher. But it's going to assume that you already know what the shape of these functions look like, and now we're just going to use derivatives to confirm and explain those shapes. So starting with our exponential functions, we are going to sketch the function f of x is e to the power of x minus 2. So this is the exponential function, and it is being translated 2 units down. So the domain of this is the set of all real numbers. So we can have x be any real number. And knowing that the exponential function itself has a horizontal asymptote as at x equals 0, then when we consider a translation of 2 units down, then we have now a horizontal asymptote at y equals negative 2. So this one should also be y equals 0 there. Okay, now the x-intercept here is given by e to the power of x minus 2 is equal to 0, which just solving here, we get that this is equal to the natural log of 2, which is approximately 0.7. So again, remember, we are working with approximate values, so 1 decimal point will be fine here. And the y-intercept, if we let x equal 0, then we get e to the power of 0, which is 1, and 1 minus 2 is negative 1. So our y-intercept occurs at 0, negative 1, and then this one is also 0.70. Now, using what we know about derivatives, the first and second derivative of this function are just going to be e to the power of x. So because that constant is not going to contribute to our derivative, and then taking the derivative of the exponential is just the exponential function. And we know that e to the power of x is greater than 0 for all values of x. So the first and second derivative are going to be greater than 0 for all values of x. So what that means is we have no critical points and we have no points of inflection. And that's kind of what we would expect anyways, right? So given our curve, which we know would look something like this, now when we translate this 2 units down, we just expect it to look something like this. So that means we don't have any minimum or maximum values, and we don't have any change in concavity. And that's exactly what we're seeing here. So no critical points from the first derivative and no points of inflection from the second derivative. Furthermore, the fact that the first derivative is greater than 0 for all values means that our function is always increasing, which again is what we expect. And the second derivative being greater than 0 means that the function is always concave up, which again is what we expect. Now we consider the end behaviors of the curve, so as x is approaching infinity and negative infinity. So we already know we have a horizontal asymptote. So as x is approaching negative infinity, we are approaching that horizontal asymptote, and this is y equals negative 2. And if you just test any value large enough, you will see that the output is greater than negative 2, so we are approaching it from above. And as x is approaching infinity, we know that the constant does not really contribute, so the e to the power of x is dominating, and we are approaching infinity here. So now we can graph the curve, and it'll be very simple. So let me I'm just going to say this is, let's do 1, 3, and then 0, 3. Okay. And then here, we can do 1. Okay, there we go. So again, just going back here, we do want these 2 points. Okay, so approximately 0.7 is going to be here. Oh, sorry, right here. And I'll do it in blue. And then we have 0, -1, and then we have our horizontal asymptote. Oh, ah, just an approximate. Okay, there we go. So then all I have to do now is draw an increasing function that is concave up going through these 2 points. If you really want to get a more precise point, you can always find f of 1, for example, or even f of 2, and then you can find f of -1 from this side. So then you have 5 points, and you should be able to get an even more exact sketch of your curve. But again, for curve sketching purposes, this is fine, and our work here is done. And then that is f of x. Now we're going to look at a logarithmic function. And again, we're just looking at the natural log here. So f of x is the natural log of x minus 2 and plus 1. So here, take a moment to consider what you know about the natural log function and what transformations you think are applied here. So we know that this -2 means that it's actually like just the 2. So we have translated 2 units to the right, and the +1 means we have translated 1 unit up. So that's also what we would expect just from transformations. But now again, making connections to the curve sketching algorithm. So since e of x is greater than 0, we know that x minus 2 is going to be 0 for the natural logarithm to be defined. So this is one requirement we have for our domain. So then the domain of the function is x in the real numbers, but x has to be greater than 2. And as such, we have a vertical asymptote as x is 2. But because it has to be greater than 0, then we don't have the case where it's just x is not equal to 2. It's actually x is greater than 2 for all values to be defined. We also can't have any value less than 2. Now, using what we know about natural logarithms, and just to give you an idea, oh, the curve looks approximately something like this. And now consider this. Oh, that's a little not straight. Okay, there we go. That's a little bit better. Okay, now I'm just going to redraw this one. Okay, something like that. Now consider this is just natural log of x. Consider this move 2 units to the right and 1 unit up. And so then we are considering the limit as x is approaching 2 from the right, it's going towards -infinity. And that's exactly what we see here. And we only have a one-sided limit here because that's what our function is defined for, x is greater than 2. Now, for example, if you also had a negative here as a coefficient, we do have to consider a reflection, so then it would be going towards positive infinity. Now we can determine the x-intercepts here, and the x-intercept is when the function is equal to 0, and this happens when the natural log of x minus 2 is equal to -1, and using logarithm rules, we know that this is e, and this is just taking, or setting these two as the exponent of e, and then we get e to the -1 to the power of -1 is equal to x minus 2. And so x is approximately 2.7. And so the approximate x-intercept occurs at 2.70. So this is one of the points we need. And this information is also important. So I'm just going to highlight the key information we need for our graphing. And now we can also find the first derivative here. So based on what you know about the derivative of the natural log, we know that this is just 1 over x minus 2, which is the quantity in there. And because x minus 2 is like its derivative is just 1, we don't have anything else, but you do have to consider the derivative for the internal function as well. Now, this value is greater than 0 for all the x values in our domain. So remember, x is greater than 2. So any value in our domain would result in the first derivative being greater than 0. So that means our function is always increasing. And again, that's what we expect from here anyways. This is an increasing function. Now we also find the second derivative here, which is negative 1 over x minus 2 squared. And now this is actually less than 0 for all x values, regardless, because this part is greater than 0, and this one is the negative, so it's going to make the whole output as negative for all x values. So then we can conclude the function is concave down, and again, that's what we expect from here anyways. So now we can graph our curve. So going back to my key piece of information, let me draw my vertical asymptote first. And here I'm just going to go with 1, 2, 4, sure. And let's do 1, 2, 3. Okay. Now this is my vertical asymptote. And then I'm going to check for my x-intercept, which is 2.7, so approximately here. And then the rest is just very simple. Oh, there we go. Just to make sure it's an increasing function, and it is concave down as we expected. And comparing this to the parent function of the natural log, if I move this down, you can see that this has been translated 2 units right and 1 unit up. And again, you can graph this yourself to see the exact graph and make comparisons to the natural log graph. And for our final example, we're going to see a sine function. So f of x is equal to 2 sine of x minus 1. So first I did want to interpret this using transformations. So we know that because of this 2, we have a vertical stretch by a factor of 2. And so our amplitude now is 2. So as we are going up and down, these are going to be 2 instead of 1. But we also have a negative 1. So our amplitude will actually be, if this is our middle, this is 2. This is also 2. And the reason I write this is because now with that translation of 1 unit down, this won't actually be at 2. It'll be at 1 because we have translated 1 down. So now use what you know about graphing trigonometric functions using transformations and have that graph. And then we're going to graph using the curve sketching algorithm, and then you're going to compare your two graphs. So starting with our domain, we know that the domain of the function is all real values and no restrictions here. So we don't have any vertical or horizontal asymptotes, which is what we would expect for the sine function. Now we find the intercept starting with the y-intercept. So when x is 0, that means we know the sine of 0 is 0. So that when our function, we set x to 0, then we have negative 1. So that's our y-intercept. And the reason why I did that first is because for the y-intercept, we actually have a little bit more of an analysis to do. And as you know, the function is cyclic, so we have more than one x-intercept. And in fact, we actually have an infinite number of x-intercepts because the function is repeating. So we know the y-intercept occurs for sure. The x-intercept is when the function is equal to 0. But for this function, this means that sine of x is equal to 1 and then dividing by, or 2 sine of x is equal to 1, and then dividing by 2, we have sine of x is equal to 1 over 2. Now this is one of our basic trigonometric properties that we should know. And this occurs when x is equal to pi over 6, 5 pi over 6, 13 pi over 6, 17 pi over 6, and repeats every 2 pi. Now, all of these values are going to be my x-intercepts. And you can also work in the negative direction as well to find more x-intercepts. Now, the first derivative from my function. So the -1 is a constant. It doesn't contribute anything. And the 2 sine of x, the derivative is 2 cosine of x. So I am going to pause here. I just wanted to highlight, again, my key points when I'm graphing. Okay. So now we also have to solve when our first derivative is equal to 0. And as you would expect for a sine function that kind of looks like this, we also have many maximums and minimums. And so we are also going to have infinite number of critical points. So for 2 cosine of x equals 0, we have that x is pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. The 2 doesn't really contribute anything here. We just look at when cosine of x is equal to 0. And this repeats every pi. So actually I should add it's 2 pi because here we add 2 pi here, or no, we're actually, it is pi because when you add pi here with the half, you get 3 pi over 2, add another pi, 5 pi over 2, and so on. So we only need to analyze one cycle of the function for purposes of curve sketching, so we consider the closed intervals 0 and 2 pi. So on this interval, we consider the critical points, the first 2 critical points, which are in this interval. And we see that in for f of pi over 2, this is 1. And f of 3 pi over 2, it's -3. And again, that's what we were expecting here when I told you the amplitude is 2, but now we have translated 1 down. So instead of it being 2 here, it's moved down and it's 1. And instead of being -2 here, it's moved down, so it's -3. And that's exactly what we are seeing here. And so pi over 2, 1 is the local maximum. And the reason for this is because, well, we can tell based on the values, but because also f prime of x would be oh, I was going to do with the second derivative, but I've done it down there, so we'll take a look at that after. So yes, this part is just based on what we know about trigonometric functions. We know that this would be a local maximum and local minimum, but yes, the interpretation with derivatives comes here. So based on the derivative, we know that f of x is increasing where cosine of x is greater than 0, and it's decreasing when cosine of x is less than 0. So that means that we can conclude from here that this is a local maximum and minimum. And also, using now the second derivative, which is actually -2 sine of x, we find that the second derivative of pi over 2 is less than 0. So we have a concave down and a local maximum. F double prime of 3 pi over 2, so the second derivative here is greater than 0. So it is positive, it's a concave up, and we have a local minimum. Now, we also have the second derivative, so we will find possible points of inflection. So this is when the second derivative is equal to 0, and this is again when sine of x is equal to 0. And this happens at 0, pi, 2 pi, 3 pi. And that's what we expect with sine anyways, with sine functions. When it goes kind of like this, we do have a change in concavity, which occurs somewhere here. And so now we know that it is at 0, pi, 2 pi, 3 pi, and repeats every pi. And so our points of inflection are these points over here. Now we can determine concavity, and so this is actually the part that confirms this for us as well, or what you know about sine functions. But the second derivative is less than 0 when sine of x is greater than 0 because of this -2. And it is greater than 0 when sine of x is less than 0. And we do have to generalize for here because there's not just one specific interval. So you are just showing you know that it works for the function as a whole. So now take a moment and sketch the graph using this information, and you should already have your sketch from transformations, and you're going to be comparing those, and then I'll show you the results as well. So here I've just set up my scale and I plotted all my points. So I have all those x-intercepts there, and I'm showing you some from the negative side as well. And then I have my y-intercept there. I have my critical points given this interval. And now all I have to do is connect these points. So this is something like this. Then we connect this one, going all the way down. And again, this would be enough for our curve sketching, but you can also consider those points of inflections as well. So we know at um, so at 0, definitely here, and then so then this one should be like there, 2 pi, pi, and then we would also have one here. Okay. Ah, but then here we're kind of going this way. And it's very hard to see when you're sketching by hand, but these tangents are increasing, and then or the concavity here is changing here. Um, and again, it's very hard to see with when you sketch by hand, but you can always graph it and double check for yourself. But again, you're just plotting those points to show that you've acknowledged that you have those points of inflections there. And so that's our final function. So just a couple of questions to end you off with. Why, or would we always pick the interval 0 to pi as one cycle, just the way I did here? So, if you remember, over here I said consider the interval 0 to pi, the closed interval 0 to pi, and is that always the case? And I want you specifically to consider sine of 2x or sine of x over 2. And so when you have a horizontal compression or a stretch, you don't actually choose this interval. The reason I chose this was because I only had a vertical stretch as well as a translation. And even if you have a reflection as well, you can use this interval. But once you have horizontal compression and stretches, so the input value of your trig function is no longer x, then you have to choose a different interval to consider one complete cycle with respect to that compression and stretch. And I also wanted to ask you, why don't we need to consider asymptotes when sketching curves of trigonometric functions, but specifically for sine and cosine? So as you know, we haven't really talked about tangent, and even in the beginning of this lesson, I didn't bring up tangents. So they do have asymptotes, but specifically for sine and cosine, why don't we consider asymptotes? And again, the reason for that goes to transformations of sine and cosine. As you know, those two functions themselves don't have asymptotes, so any reflection, translation, stretch, or compression that you do vertically or horizontally, then we are not actually adding any asymptotes in there. So that's why we don't really need to consider any asymptotes. But for example, here we do consider amplitude. And we do have a cyclic property, which other functions, for example, don't have. And that is our final lesson on Unit 4, curve sketching. So you have lots of practice here with these functions, but do focus more on polynomial and rational functions for your assessment next lesson. But as always, if you have any questions, don't hesitate to reach out and check your answers with graphing tools. And I will see you all in our next unit.